Hello class, this is CSE-5250, Section 61, Week 5, Fall 2024. CSE-5250, it's been a while. So, due to circumstances beyond my control, I have been reassigned CSE-5250. Well, CSE-5250 has been reassigned to me. So, we're going to look at parallel programming the way I would look at it. So, really the biggest problem with all this is the fact that we're transitioning from one professor's teaching style to mine. So, I do understand that you had a few assignments given to you already. Basically submit what you have even if you're lost. We're going to cycle back to that once we get to MPI. I made an announcement on Canvas outlining what we're going to do for the term, and basically it's going to be in a different order than what the textbook, and we are going to be using the same textbook, Introduction to Parallel Programming. We're going to be looking at that, but in the order that I personally think is easier to look at. So instead of going through the book linearly, we're going to be jumping from chapter to chapter. So chapter 4 is the first chapter that I would like for us to look at. That is all about p-threads. Do not worry if you don't know how to work with p-threads. And if you do know how to work with p-threads, then the next set of slides, which is intended as review, will be review for you. And if you are concurrently taking CSE-4600 with me, then you'll notice that these are literally the same exact set of slides I had made for CSE-4600. It's just that this set of slides contains content for CSE-4600 that I have yet to record. So yeah, I might be repeating myself. Oh yeah, and your first assignment with me as the instructor, it's simply going to be a Hello World program. So if coincidentally you are concurrently taking CSE 4600 and CSE 5250, and you already did the lab assignment for 4600, and I asked for you to do the same thing for 5250, you can just resubmit your existing assignment. But anyway, really, I never expected that I would be back teaching CSE 5250 so soon. And more to the point, I never expected it would be done so suddenly. So I had to, in a rush, start creating course material for CSE 5250. Even though I have the slides for it already, I need to transition from one teaching style to mine. And that's why, and especially now that I'm teaching CSE 4600, that is operating systems, we have a starting point from another class that we can use to springboard into CSE 5250. So these slides are basically review. Now, my point is, the other thing is this. It does not matter if your operating systems textbook is the one that with the Carnival. This is Tannenbaum's operating systems book, 4th edition. And this one is Silvershot's operating systems book, 10th edition, the one of the dinosaur. Doesn't matter which OS book you're using, it's all going to have the same base concepts, just arranged in a different order. So, this is going to be chapter 2 of the operating systems book with the Carnival. So basically, review of processes and threads and the challenges that they bring when you introduce multi-threaded programs to a computer system. So, the most central concept of an operating system is the process. This is an abstraction of a program that is running, and yeah, you're going to have multiple programs running at once. So how is your computer able to do all that? It's through the magic of something called a context switch. That is where the operating system switches between processes to process very fast. That it, even if it only has one CPU core, it provides the illusion that it is running multiple things at once. These days we have multi-core CPUs, so it might be able to run multiple things at once, concurrently, without having to fake it. The key thing to know about processes is that they can be interrupted and returned to at a later point. Much like this scenario that I'm going to show you here. Imagine you were baking a cake and you had the instructions laid out in front of you with the ingredients and tools also laid out in front of you. You follow the instructions, sift in flour, add milk, all that, egg, and right before you're about to pour the batter into a cake tin, your son comes in screaming that he got stung by a bee. In this scenario, you would take a mental note of where you are in this process of making a cake. You then get your first aid kit and administer first aid to your son. That is the important thing about a process. You can stop a process anytime if something else happens that you need to tend to. Think of a process as an activity. Something that can be interrupted by something else that you can return to later. A program by itself on a computer does not do anything until it is loaded into memory. And that's what makes viruses so insidious. They don't do anything until you do something with the source code. Or the malicious executable. So here's why we would have processes, which the Tannenbaum textbook calls processes in a process. These are called threads. Here's why we would have multiple threads in a program. A program may have multiple things happening at once, and some of these block from time to time. What makes threads different is the following. And I guess my face cam's cutting part up. Here we go. So, here's the point about a thread. When we have a program running, there might be parts of it that need to be running that are essential for the computer's operation. Such as a word processor, where one of the threads is periodically updating the content on the screen, and another thread is saving the file onto a disk, and a third thread is the thread that is listening for computer input. If we only had one thread to do all of that, every time you tried to do something with the Word document, say make big edits such as delete the first page, you cannot type anything until the document as displayed on the screen is updated. And if you are trying to save, if you're trying to type onto that document while that program is auto-saving, you can't. That's why we have multiple threads. The key thing about threads is this. Threads that are part of the same process all share the same address space. That's data and instructions. Threads are more lightweight, so they are easier to create and destroy and context switch than processes. If we have multiple threads as part of the same program, and one of them is blocked, because there are multiple threads, there is always going to be some part of the program that is still running even if parts of it are blocked. Unless all the threads are blocked, then the program can't run anymore. And oh yeah, if you have a multi-core CPU, which I am betting you have, then you can run multiple threads at once. So, a rather fun analogy that I have for multi-threading is, imagine you were building a Lego train. Can you tell I like trains? Can you tell I like Lego? Anyway, you can imagine this big activity of building a Lego train as a process of building the train brick by brick, car by car. You might also have some non-train accessories such as a train station. The point is, we have instructions and we have stuff that we need to work with. You can build the train yourself, but it's gonna go much faster if we have a second set of helping hands. So, multi-threading is where you had your friends build the train for you, by, for example, each building a different train car. So you might be building the locomotive of your train, and then others might be building, say, passenger cars. Or if this is a freight train, we would have different types of cars, tanker cars, box cars, those cars that hold storage containers. And if you're really old-timey, you would throw in a caboose. We don't have cabooses anymore because, well, there really is no need for them anymore. The point of a caboose on a train is to make sure nothing bad is happening between the front and the back. We have wayside detectors for that, and something called it's a little device called an end of train device that says this is the end of the train. If you see that device is missing, that means part of the train has detached. Like, what is this? You and your friends are building a train, but you're each building a different car in the train. The reason why we can do this is it doesn't matter if we build the passenger cars first or the locomotive first. If we have stuff like that where we can do these kinds of things in any order and it doesn't affect subsequent operations after that, if we can do that in any order, then we can, in theory at least, do those things at the same time. If we can build a passenger car, if we can build a locomotive and have that not affect building the passenger car, then we can build them at the same time. So, the POSIX threads library, or pthreads as it's called, this is a big library with like 60 functions, and we are gonna be using them to write our first multi-threaded program. So, the first set of functions are for creating threads, terminating threads, and joining threads. So, and there's also a set of attributes associated with pthreads as well, and we can create the set of thread attributes using attribute init and attribute destroy. My point is this: when we want to create a thread, obviously we call pthread create. The thing about pthread create is that you can pass in a function into that. You can pass in a function into that pthread create function, and basically it'll tell the thread what to do. So, pthread create and pthread join, those two functions are based on something called the fork and join model, where, in the case of pthreads, there is a main thread that is the first thread that runs in the entire process. The main thread forks a bunch of threads. Those threads do work, and when they're done, they join back with the main thread. At the end of the program, we want to call pthread exit. That way, it signifies to the system, we're done with this thread, we don't need it anymore. Yeah, so the fork and join model. It's not in the operating system's textbook, but it is in the parallel programming textbook. Also, in operating systems, there are built-in mechanisms for determining which process to run next. So at one point in time, your system might be executing Discord, and then another instance of time it might be executing, say, PowerPoint. There is no such mechanism at the level of threads. So you as a programmer must determine when to have threads release the CPU to other threads. We do that using pthread yield. And yeah, I mentioned this before, pthread has attributes associated with them. Those are created and destroyed using attribute init and attribute destroy. Here's the thing about processes. As far as processes are concerned, they think they have the entire computer to themselves, even though there's only one computer's worth of resources to go around, and they're being shared by other processes. That's it. It's very common. It's quite common for processes to communicate with one another, and that means of communication is called interprocess communication, or IPC. There are a few issues regarding IPC, how to pass information between processes, making sure processes don't get in each other's way, and making sure operations are done in the correct order. The first part doesn't really apply to threads because threads that are part of the same program share the same memory. So it's very easy for threads to share information between one another. In some systems, processes that work together may share some common storage that they can read and write to, and that can cause problems. Let's say we have a directory full of files that's to be printed, and periodically something called a printer daemon comes in, takes one of these files, and sends it to the printer to be printed. Let's say two processes come in and they want to write something into one of these slots in this so-called spooler directory. Process A comes in, reads the value of in that says slot 7 is the next available slot. And right as process A is about to write its file into that slot, process B runs next, reads the value of in and says, oh, I'm going to write my file into slot number 7. And then process B is done, and then process A runs after that. Process A still thinks the next slot is slot number 7. So what it does is it writes its file into slot 7, overwriting whatever file process B had written into slot 7. So process A's file gets printed, and process B's file never gets printed. This is called a race condition. It's called that because processes are racing one another to be last. In a race condition, last place wins. I say this quite a lot, don't I? And yeah, we might have the potential of debugging race conditions in parallel programming. I'm just gonna say, just be prepared to start debugging these things. They're sometimes called race hazards, by the way. You know that song where someone got an edgy 13 tattoo, but the tattoo parlor screwed up by drawing a 31? Maybe it's through the power of race conditions that screw up happened. So we avoid race conditions by doing this. We keep processes from... We make it so that only one process can access that shared resource at a time. When a process tries to access a shared resource, it's executing some code that is part of what is called a critical section. So really what we need to do is make sure that only one process is executing its critical section at a time. And the means at which we make it so that only one process can execute at a time, that is called mutual exclusion. So if we had mutual exclusion with our spooler example, that means A is writing its file into slot 7 of that spooler directory. If process B tries to write its file into the same slot as process A, it's not going to. It will be blocked, and it won't operate until process A leaves its critical section. So one important thing to note here is the operation in which process A wrote its file, it got interrupted. We cannot interrupt that operation. So A enters its critical section and B cannot until A leaves. Once we have that, we have solved the race condition that we had previously where process A's file got printed, but not process B's. So there's several ways to enforce mutual exclusion using something called busy waiting. I'll explain why busy waiting is not a good idea, but this is something called Peterson's solution. It is a software-based implementation of enforcing mutual exclusion. Basically, we have two processes and they take turns entering this critical section. When one process enters the critical section, it calls some function that says, I'm entering my critical section. If anyone else is trying to enter the critical section, you're gonna get blocked. Well, in this case, they're not gonna get blocked in the sense of blocking on an operating system. Rather, what they're going to do, what's gonna happen is if a process tries to enter its critical section while another process is already in the critical section, it's gonna get caught in a loop. It's gonna get caught in a loop. So process 0. So imagine this. Neither process is in its critical section, and then process 0 wants to enter the critical section by calling enter region. When you call enter region, you have to pass in your process ID. So this is going to be a process number. So in this case, there are two processes. It's going to be either 0 or 1. So process 0 enters its critical section. It passes its ID of 0. No other processes are running. Process 0 is free to enter its critical section. Process 1 then wishes to enter its critical section, while process 0 is already in its critical section. Basically what happens is, process 1 is going to hang until process 0 leaves. In the case that both processes try to enter their critical sections at the same time, whoever prevails is the one who made their modifications last. So that's what's meant by last place wins. I am glossing over a few details, by the way. I just want to condense this in a format that I just want to have this information in a condensed format. So this is enforcing mutual exclusion, and one of the things that we'll be looking into, or one of the things that we might be discussing regarding pthreads is something called the producer's consumer's problem. It's also called the banded buffer problem. Basically, we have two processes, or possibly two types of processes. One type is the producer. It puts data into a shared buffer, and the other one is a consumer, which takes data out of a shared buffer. So the problem arises when the producer tries to put something into an already full buffer. The operating system's solution to this is to have that process go to sleep, with the idea that once a process, that is the consumer, takes something out of the buffer, it's going to wake up the producer so that the producer can put stuff into the buffer. Likewise, if a consumer tries to take something from an empty buffer, it will go to sleep with the idea that the producer will put something in the buffer and then wake up the sleeping consumer. How weird would it be if you go to McDonald's, no one's there, and you go to sleep? And then a McDonald's employee wakes you up and says, "Hey, you ready to order?" Okay, so a possible implementation might look like this, but there is actually a problem in here. We have the potential of a race condition because the access to count, that is the number of items in the buffer, access to that is unconstrained. So consider this scenario. The buffer is empty and the consumer has just read the count to save of 0. The scheduler then decides it's now the producer's turn to run, and the consumer stops running. The producer adds an item to the buffer, increments the count, and notices it's a 1. The producer reasons that the consumer must be sleeping, so it calls wake up, even though it's not asleep. It's actually in a not ready to run state because the CPU scheduler deemed deemed it necessary to remove the consumer. So it's not asleep. It's in this unable to run state. So since the consumer is not asleep, that wake-up signal is lost. So when the consumer runs again, it will test the value of count, see that it's 0, and go to sleep. Basically what happens is both processes go to sleep and there's nothing to wake them up. We can resolve this by using a wake-up waiting bit, but there is another way to resolve this. It's called a semaphore. So, in 1965, Edgar Dijkstra suggested an integer variable to count the number of wake-up signals saved. So a semaphore is really just a thing that signals. That's what this weird naval thing is here. So, semaphores are just a thing that signals. A signaling thing. Kind of like a traffic light. Oh, have you ever noticed that railroads have railway signals that look like upside-down traffic lights? That is a holdover from when railway signals were just balls on strings. So, if the ball is up, you are said to have the high ball, and that's why green is up on those railway signals, at least in the US. Oh yeah, if green is up, that means you have the high ball, it means you're clear to go. So yeah, semaphores are just things that signal. What are we trying to signal? Well, we'll see. So Dijkstra also proposed two operations on semaphores. They're usually called up and down. Down decrements the value. So the down operation checks to see if the value is greater than 0. If so, it decrements the value and continues. If it is 0, then the process goes to sleep without completing the down operation for the moment. The up operation increments the value of the semaphore. If a process was sleeping on that semaphore, unable to complete an earlier down operation, it's awoken so it can complete its down operation. And if there are multiple sleeping processes, then one of them is chosen to wake up. The important thing about either the up or down operation is that they are atomic operations. They are done as a single operation that cannot be divided up into anything smaller. Atomic in the sense that, no, it's not gonna irradiate you and make you turn into the Hulk. Atomic in the sense that we cannot divide it up into anything smaller. Like how atoms are called atoms because the idea is we cannot cut them up into anything smaller. Well, you can. Technically, you can cut up a uranium nucleus into smaller pieces, but at that point it stops being uranium. So if we are to solve the producers-consumers problem using semaphores, we might have code that looks like this. So here we have 3 semaphores. They are signaling whether they're here to signal how many empty slots in the buffer there are and how many full slots there are in the buffer. So there are 3 semaphores. 1 to indicate the number of full buffer slots, 1 to indicate the number of empty buffer slots, and a third semaphore that's called a binary semaphore because it can only ever be the value 0 or 1. We use this, called mutex, to enforce mutual exclusion. And that one controls access to our critical section. Because remember, only one process is allowed in its critical section at a time. As long as each process calls down before entering its critical section, followed by up after leaving its critical section, we can guarantee mutual exclusion. When we use semaphores like this, we are using them for synchronization. If a semaphore's ability to count is not needed, we can just use a binary semaphore. In that case, it's now called a mutex. A mutex has 2 procedures that go alongside it. One is called mutex lock, the other one is called mutex unlock. When a process needs access to a critical section, it calls mutex lock. If it's unlocked, the process is free to enter its critical section. If it is locked, then the process is blocked until another process calls mutex unlock. When the process exits its critical section, it then calls mutex unlock. So if there were any blocked processes, they will be unblocked at this point. So due to their simplicity, this is a assembly code implementation of how a mutex lock and mutex unlock procedure may be implemented. These are using some assembly instructions, by the way. So unlike the previous code, which uses a... So unlike the previous code that uses a busy waiting, and this is the busy waiting here. So if you are a process that wants to enter your critical section, you test and set a lock, see if the old value was 0, and if it was not, you go back to the beginning and do it all over again. And you do that again and again and again in a loop until some other process calls leave region, stores a 0 in the lock, so that when you test that lock again and the previous value is 0, you can enter your critical section now. And again, with mutexes, instead of a busy waiting, a thread that's unable to acquire the lock calls thread yield. That gives the CPU to another thread so it can run in the meantime. And yeah, the final part of here has to do with how this improves performance on the level of an operating system. Neither mutex lock nor mutex unlock require any kernel calls. This makes it very fast and very easy for threads to synchronize, since we don't have to get the kernel involved. If we don't need to get the kernel involved, then we increase system performance. That's more important in the context of operating systems, however. The one caveat to all this is this. Threads have no problem accessing the same mutex since they have access to the same address space. Remember, threads have access. Threads of the same process have access to the same data and the same variables. No, they have access to the same data and the same instructions. If there is a shared variable, such as a mutex, they can share it no problem. The problem is, what if you have two processes on two different machines and they need to talk to one another? Well, before we get to that, what if you have two processes and they need to talk to one another? Well, there's several ways to do that. One of them is these two processes can have a piece of shared memory between the two, and they'll just read and write to it, and that's how they share information. Otherwise, they might just have to use a shared file. So, mutexes in pthreads, there are a few functions related to that. Pthreads, if you are to make a mutex in pthreads, you use pthreads mutex init. If you don't need it anymore, you use pthread mutex destroy. We can lock a mutex using pthread mutex lock if the mutex is already locked. A mutex is basically a lock. Someone needs to get a lock so they can lock themselves into the critical section, and when they're done, they'll unlock it, free themselves, and then hand the lock to someone else so that they can lock themselves into the critical section. The reason why we need a lock is so that no one else can enter the critical section, because remember, one process at a time in the critical section. So a mutex can be locked using pthread mutex lock. If it's already locked, then that thread will be blocked. Instead of blocking, a thread can instead call pthread mutex try lock. That returns an error code, and that allows for a process to do what's called busy waiting. I talked about busy waiting earlier. That is where if a process is trying to enter a critical section when another process is already in its critical section, it will just enter an infinite loop. I'm talking about processes, but really I should be talking about threads. a lot of what I'm saying applies to both processes and threads, but since we're going to be entering the world of p-threads, hopefully in a greater depth than what operating systems can provide, it's important to know that we're talking about threads. And then pthread mutex unlock releases a mutex and releases it if there's at least one thread waiting for it. So there is another synchronization mechanism called a condition variable. Whereas mutexes are good for allowing and blocking access to a critical section, condition variables allows threads to block if a certain condition is not met. So we create and destroy condition variables using, well, pthread cond init and pthread cond destroy. The primary operations for condition variables are pthread condition wait and pthread condition signal. They are atomic operations, and they're like the wait and signal threads. They're like the wait and signal operations that we've seen before. The blocking thread is often waiting for the signaling thread to do some work, release a resource, or perform some activity. Only then can the blocking thread continue. Also, if there are multiple block threads, then we use pthread condition broadcast instead. So, condition variables and mutexes are always used together in the following way, such as with this modified producer's consumer's code here. One thread tries to lock a mutex. If it can't do that, then it waits on a condition variable. Eventually, another thread will continue. Another thread will signal it, and it can continue. It's for this reason that one of the parameters for pthread condition wait is a mutex. And hopefully we're gonna see that when we get to chapter 4. It should be noted that condition variables, unlike semaphores, have no memory. If a signal is sent to a conditional variable on which no thread is waiting, the signal is lost. You gotta be careful here. And finally, one of the things that we need to know when it comes to inter-process communication is message passing. When you have two processes on two separate computers, they cannot share memory. So the only way they can talk to one another is using message passing. We need two functions for this: send and receive. These are system calls, and they can be made, and these are system calls, and we can turn them into library procedures. So send is going to send a message to some process, and receive is going to receive a message from some process. And there are unique challenges. There are unique design issues. There are design issues unique to message passing. One, the message can get lost in transit. So, as a safeguard, the receiver can send an acknowledgement message back to the sender, but then that could also get lost. So we need a way of resending that message, and if the sender received more than one acknowledgement message, it needs to be able to distinguish old ones and new ones. Also, it's possible for a message to be sent to an imposter. To protect against that, you need authentication. You need to make sure whoever it is you are sending this information is the real deal. And finally, sometimes the sender and receiver will be on the same machine. The thing about message passing is that it's slower than other means of interprocess communication. It's just that if we have a computer that wants to send a message to another process on a different computer, such as the case with what are called distributed systems. A distributed system is merely a group of computers connected to a network, and they all talk to one another. They all are working on some big task, such as protein folding. Ever heard of folding at home? Back a few years ago when we had the COVID-19 thing, there was a spike in usage for folding at home because so many people were at home, so many people had access to their computers that they just basically they contributed their supercomputers resources to this folding at home effort to figure out what makes COVID tick. And at one point, it became the world's most powerful supercomputer. So yeah, that's the power of message passing. It's also true that we were able to get pictures of black holes. Anyway, if we have the producers consumers code, if you want the producers consumers problem solved using message passing, the code might look something like this. And MPI, we won't be getting to MPI until later into the term, but basically this is a message passing interface. I mean, it literally is called message passing interface. So, oh yeah, the last means of synchronization is called a barrier. You're gonna see barriers. You might see barriers when it comes to parallel programming. Basically, sometimes you'll need processes to proceed to the next step together. So you need to make sure they are moving together at the same time. So it's kind of like a traffic light. So, processes arrive at the barrier at different times. Once all the processes have arrived, the barrier lifts and they all proceed together. And an application of a barrier is the following. Have you ever been stumped on matrix multiplication before? I have. But to me, what made matrix multiplication click for me is the fact that matrix multiplication is just a whole bunch of dot products. So basically, if you have two square matrices, the product matrix is going to be, well, the same size as the two matrices, but its entries are going to be dot products. Matrix multiplication is nothing more than doing a whole bunch of dot products. It's going to be a lot of dot products though, but basically it's this. If we have some matrix A, we can turn it into 3 row vectors, and matrix B, we can turn that into 3 column vectors. The entries of the product matrix are nothing more than the dot products of the first matrix's the first matrix's row vectors. It's a dot product of one matrix's row vectors and the dot products of the other matrix's column vectors. Basically, if you can do a dot product, you can do matrix multiplication. Of course, it's going to be a lot of matrix multiplication. The 3x3 example is still pretty small, but still that's a lot of work. You have to do how many multiplications? It's a lot. And then you have to do addition on top of that. The point is this. If each of these dot products are assigned to a different process, then we need to make sure that before we do anything after that, every dot product is calculated. So that is a barrier. And the reason why I talk all about this is because chapter 4 of the book parallels these concepts. And in particular, we have processes, threads, and p-threads. The differences between processes and threads. We have a hello world program, how to start threads, how to stop, run threads, how to stop threads. We have the fork and join model. We have matrix multiplication. We have the concept of a critical section in here. That's section 4.4 of the book. We have the concept of a busy waiting. That's section 4.5. We have the concept of a mutex. That's section 4.6. And then we have the producer-consumers problem and semaphores as in section 4.7. So that's why, oh yeah, and we also have barriers in here too. So really, what this filler emergency lecture is here is just a preview of what we're going to do in parallel programming. So I would like for us to try a few programming assignments in here in p-threads rather than NPI first. So we're gonna what I'll have you do is I'm going to give you a sort of introductory assignment to pthreads. And if you are taking CSE 4600, you'll notice it's basically the same assignment. You are making a Hello World program using pthreads. After that, we can delve into more advanced topics regarding pthreads and all. And then hopefully, once we have that under our belt, we can start looking at OpenMP. And if you ask me, OpenMP is one of the more fun ways we can parallelize a program. Though there are several caveats to that. We can only parallelize certain things. We can parallelize a for loop, but it has to be a specific type of for loop. We'll get more into that later on. But yeah, our first chapter that we're going to be looking at is going to be chapter 4 in the book. So we are not going through this book in order at all. So chapter 4 of the book, that is page 159. We are going to begin with pthreads. So that's going to be a bit of a review from concepts and operating systems that's going to parallel our discussion on pthreads. So, if you have any questions on what we're going to be doing over the course, don't hesitate to email me. So, with that, I would like to thank you for your time with watching this video. I hope this gives you a good idea of what we're going to be doing. And if you have any questions on any of the programming assignments, definitely reach out to me. Email me. I do not have office hours, but you can schedule a Zoom meeting with me, and we can talk it over Zoom. If you are lucky enough to catch me in one of my other classes, we can talk it over there too. Alright, so that's going to be it from me. Expect your first new assignment sometime in the coming days. It's going to be a Hello World program that uses pthreads. And it's basically going to be the same assignment from CSE 4600. If you've never done pthreads before, then this might be a good introduction for you. And if you have done pthreads before, then this is going to be a good review for you. And if you are taking the same CSE 4600 class that I am teaching, then you can just resubmit the same assignment. Alright, I'll see you in the next video. Take care, and hopefully we'll begin our proper discussion on pthreads. Alright, take care, everyone, and have a good one.